Today we're going to take a look at section 7.3. It's titled Repeating Decimals. In particular, we talked about terminating decimals last time. And what was it, our condition for when a fraction could be written as a terminating decimal? What did it take? It took what? 2s and 5s. Where, AK? Okay, so you're right. So this was actually theorem 7.1, just so you know, as a reference. It said if, the reduced or simplified fraction, or we'll say fractions, denominator, contained only factors, let me say it this way, only prime factors, because it will contain other factors potentially, only prime factors of 2 and or 5. So it could have 2, it could have 5, or it can have 2 and 5. So what then if you can't? Right? What if it's not terminating? What then? Well, if the fraction is an integer over an integer, hence it's a rational number, right? And does not terminate then it repeats. So, sorry, you guys are probably still writing a little bit. I'm sorry about that. So we're going to do an example. I know this is going to be repeating because why? There's a 3. Yeah, 24 evenly divides by 3. 3 is not 2 and it's not 5. So yeah, this is going to be a repeating decimal. So we're going to actually find the decimal representation and sort of examine when and how we look at the repeating part. So we're doing 1 divided by 24, but of course 1 doesn't divide by 24, so I need to put in a decimal point. If I think about that number as the number 10, it doesn't work either. It goes in 0 times, so I need another decimal point, or number after the decimal point, and I have the number 100 for the purposes of thinking about it, right? How many times will 24 go into 100? 4 is correct. What is 4 times 24? 96, very good. And if I subtract, I get the number 4. So I'll put another 0 and draw it down, or bring it down. How many times will 24 go into 40? 1. 1 times 24 is 24. If I subtract, what do I get? 16. And we will bring the number 0 back down again. All right, so at this point, you know, the number's getting a little bit bigger. How many times will 24 go into 160? It is 6. What is 6 times 24? 144. And if we subtract, what do you get? 16. Now, we already had a 16 as a remainder once before, didn't we? In exactly the previous step. The remainder here and the remainder here matched. Once that happens, we've actually pushed ourselves into a repeating decimal position. Okay, if I try to do this again, I'm going to bring down another 0. I'm going to get another 6 besides the 6 that's already at the top, right? And it's going to keep happening. So if you don't happen to notice the point where the remainders match, you will notice that you're starting to repeat the digit at the top that you get as your dividend every time. But if you happen to notice that it matches here, you can stop here and know that the last time you had the repeat bar, or last time you had the remainder that repeated now, is where you're going to get your repeating bar. So in our value here, we want to be careful that we actually put the repeating bar only over the part that repeats. In this case, that's simply the number 6. Now, I'll show you an example here in a moment when it's not just one number, because it's not always one number. Sometimes it's 2 numbers that repeat or 3 numbers that repeat. And actually, there's an example, I don't know if we do it today or not, where there's 6 numbers that repeat. You have 6 numbers before it actually gets to the repeating part, okay? So sometimes you have to go quite a few steps before you actually see the number repeat. But once you do, you have the ability to put the bar on the top. We call this type of a decimal a repeating decimal. The repeating block of digits is the repetend. So the repetend on the last problem was simply the 6. And there's, of course, a note here that's really important. I expect to see division. Now, you have a calculator. Should you check your work? Absolutely. You should know when you're done with this problem that you did it right, because your calculator should match your written work. But I still expect to see your written work all worked out. So we're going to do another example where it isn't just one repeating block or one repeating number in the repetend. We're going to do 29 over 99. Now, you may know a shortcut to this. We'll talk about this particular type of a number, namely the fact that it's over a 99 in a moment. But I want to just do the problem out, because for the purposes of what I'm wanting to show you is I want to show you why it's just not one repeating number on this one. So we're going to do 29 divided by 99. Of course, 29 doesn't go into 29, so I need a decimal and a 0, and there's my decimal point. So 99 will go into 290. How many times? 2. What is 2 times 99? 198. And if I subtract, what do we get? Yes, 92. Okay, so I have a remainder still, so I'll bring another 0 down. 920. How many times will 99 go into 920? It's 9. And 9 times 99 is 891. And if I subtract, I get 29. That's actually my stopping spot, if I notice it quickly enough anyway, because that's the same 29 that I had earlier. But notice it took 2 subtraction steps, 2 division steps, however you want to think about it, before it started to repeat. What that tells you is that there's 2 numbers that it would take to repeat. And again, if you aren't sure, just do another couple of division steps, and you'll see very quickly that it's the 2 and the 9 that are repeating themselves. So you end up getting the number 29 hundredths repeating. Okay, so what we've done so far is we've taken fractions and we've turned them into repeating decimals. I want to show you how to take a repeating decimal and turn it back into a fraction. It's always good to be able to go 2 directions with things, so we're going to go the other direction now. This is likely something you haven't done before. Probably not anyway. So we're going to take the number 0.61 repeating. There is a shortcut to this one, but I'm not interested in showing the shortcut because I want to show you how it works all the time and not just in special cases. So what we're going to do is we're going to set the letter N, just doesn't have to be an N, but I use N's. Okay, so the letter N, and it's going to equal that 0.61 with the repeating bar on top. Okay, so we're just starting out the process and we're giving it a name. It's called N. Okay? All right. The repeating part has 2 digits that repeat. Agreed? The bar's over both of them. So we're going to multiply by a power of 10 that has 2 zeros. That's the number 100. If I had 3 numbers repeating, I'd multiply by 1,000 because it has 3 zeros. If I had 1 number repeating, which I will in a moment, I'd only multiply by 10. I only need to multiply by however many zeros in the number that's a power of 10 that I have places that repeat. Okay? That is the most common mistake people make on this type of problem, is not knowing what number to multiply by. Okay, so on the left, 100 times n is 100n. On the right, I want to write this out for you a little bit out here. This number looks really like this, right? And it keeps going. Agreed? Okay, so if I multiply by 100, it moves the decimal 2 places to the right, which gives me 61.616161, on and on, right? So this actually gives me 61.61 repeating. I can't put the repeating bar on the number before the decimal, right? It doesn't work like that. So I'm going to put it on the parts after the decimal that still repeats. Now this is really important. This is 61.61. And this is the reason that I multiplied by 100. Because one could say, well, why don't you just multiply by 10? If you do that, you're going to get 6.16, and then I've got 16 repeating. And here's why. I want these to match. And they need to be in the same place with the same repeating bar. They need to be perfectly identical after or under the repeating part. Okay? And here's why. We are going to subtract off not the repeating part per se, but the original value. Okay, so n is equal to 0.61 repeating. So I'm going to subtract n from the left because the left-hand side has n's, and I'm going to subtract the 0.61 repeating from the right because it has 0.61 repeatings on the right. I'm allowed to do that because in an equation, as long as I do the same value to each side, that's a legal operation. But n and 0.61 repeating are identically the same. Look different, same value. So on the left-hand side, what do I get? 99n. And what do you notice happens on the right-hand side? You get 61. Indeed. The last step is to divide by the 99. We would want to make sure that 61 and 99 don't have anything in common. These don't. If it did, we would reduce the fraction, and we're done. Okay? So, example 3 and example 4 are very similar. You have both of them on their page there together, so I'd encourage you to look on the page itself. How are they different? Yeah, you're right. The repeating bar on example 4 is only over one digit, the number 1. So, just as a reference point, this number looks like this instead. Okay, does that make sense? It's not the same number I had before because I only have the repeating bar of the 1. Now, the process is the same. N equals 0.6, 1 is repeating. All that's the same. But this time, I only have one number repeating. So I need to multiply by a power of 10 that only has one zero. That's simply the number 10. Okay, is everybody with me so far? Again, the most commonly missed piece when we do these particular problems from my, I don't know, almost 8 years, I feel like, of teaching this particular section, is people not getting the number they multiply by right. And then things don't line up, and then they get stuck, and they're like, I don't know what to do now, okay? Got to get them to line up right. So over here, and if it helps you to write it out, kind of like I have over here, do that. We are multiplying by 10, which means we're only moving the decimal one place. Now, I want to show you something. That gives me 6.1 repeating. That's what this is. But I really want the repeating bars to line up. So while it is correct to write it this way, it is more helpful to write it like that, because then the repeating part lines up. Another confusing part here. Okay? We want the repeating parts to line up. So I'm going to end up writing this over here as 6.11 repeating, and I have 10n on the left. The The next step is always the same. I'm subtracting the original thing that I started with. N on the left, and in this case, 0.61 with the 1 repeating on the right. So I have 9n on the left. These 1s, they go away, right? What is 6.1 minus 0.6? 5.5. My last step would be to divide by 9. And I'm sort of kind of done. I'm actually not done on this one because if you take a look back up at the directions, how did it say that the form is supposed to look when I'm done? A over B where they are what? Integers. 5.5 is not an integer. Okay? But it's easy to fix. Check it out. If I multiply by 10 on the top and bottom, then all of a sudden I actually have integers 55 and 90. So I can fix this really simply. Of course, in doing so, you might recognize now that they have something in common that we can divide by and should divide by. So what do 55 and 90, have in common? A 5. So we'll divide them both by 5. 55 divided by 5 is 11. 90 divided by 5 is 18. So, how can you check your solution? You grab your calculator and you type in 11 over 18. If you have it with you, do that real quick. If we did it right, you should end up with 0.6, 1, 1, 1, 1, 1, 1, all the ones that you see across your screen repeating. Did it work? Fabulous. All right, I want to show you an interesting fact, something you may not know on the next example. So we're going to do the problem again. Now we have the number 0.9 repeating. The process starts out the same way, n equals 0.9 repeating. And of course, we recognize that that's this number like that. So Kaylee actually mentioned this number last time when we were talking about 7.1 homework. I think you were asking about whether or not there's a largest number bigger than 1 that's a rational or a decimal number or something like that. And you mentioned this number, and it was just all I could do to keep my mouth shut when you did it because you were just leading so nicely into this particular lesson. So, how many numbers repeat? 1, right? Yeah. So what are we going to multiply both sides by? 10. You got it. A power of 10 with 1 0, that's the number 10. So on the left, I end up with 10n. On the right, what am I going to end up with if I move the decimal 1 to the right here? Yeah, this one's simpler than the last one because the repeating bar automatically sort of falls in the right place. So it's 9.9 repeating. Okay, all good so far? What's my next step? Subtract the original, which is n from the left and 0.9 from the right, 0.9 repeating. Have 9n on the left. What do I have on the right? 9. And what will we do? We will divide by 9. And what do we get? Did you know that 0.9 repeating was equal to 1? It is. There's no tricky math. I didn't do anything that's illegal. Everything is absolutely 100% correct. 0.9 repeating is simply another way of writing the number 1. I don't know why you'd want to write it that way, but it is. It is another way of writing the number 1. Cool fact. All right. Let's take a look actually at a couple more where we actually are asked to find numbers between other numbers. Kaylee.
So at the store when things are $1.99, does that mean like it's actually, is that like a rate that they use?
It's not because $1.99 terminates. The 9s don't repeat forever. Same's true even at the gas station, right? When they have that third 9, it's still not 9 repeating forever, although it's probably close enough that we I mean, really, like when you guys see $1.99, do you think $1.99 or do you think $2? I think $2. So it's not quite the same thing, although it's very close. Yeah. All right, this one says to find any decimal between 0.9 repeating and 1.1. So what did we just say that 0.9 repeating is? 1. So this particular question is simply asking us to find a decimal value between 1 and 1.1. All right? Now, I'd like to show you, even if you know how to think about this without any trouble right now, I'd like to show you a quick and dirty way to do this in case it is a number that looks a little bit funky and you're like, I don't quite know what to do with that. So we're going to actually pretend like the 0.9 repeating, we don't know what it is. Because my goal when you see this question is not for you to actually have to know what the repeating decimal is that they give you in fraction form. That's not the goal. What I'm going to have you do is to take that value and just write several of the repeating parts. Okay? If it had said like 0.37 repeating, you would have written 0.37, 37, 37, 37, like that. Okay? So whatever they're giving you, just write out, 6 of them or something like that. And we're going to add that to the other number that they give you, 1.1. And you can divide by 2. This actually gives us the halfway point. I'm actually answering part B. My bad, I'm sorry. That's what happens here. Okay, let me move it down. You guys just draw arrows. I'm answering part B. Grab a calculator. Type in 0.9 lots of times. More times or less times than what I have. It doesn't even really matter that much. Add the 1.1 and divide by 2. What do you get? Okay, 1.049 repeating. But what do you suppose 49 repeating actually means? Say again, Kayla, I can't hear you.
1.1 divided by 2.
Nope, it's not 1.1 divided by 2. That number would be smaller than 1.1, like smaller than 1, actually. This is the same as the number 1.05. It's that 9 repeating thing again, right? It is. That 9 repeating means that it's actually the next value 1 higher, just like it is for 0.9 repeating with the actual just by itself. Okay, so you can actually do this with any number. So if you get, I don't know why I put 1. Let's say you did 3.07 and the 9, there we go, and the 9's repeating there. Well, this is just another way of writing 3.08. Okay, what does it do? It takes the number that's before it, and it's 1 higher. Now, let's go back and actually think about this for finding any decimal between. We said this was the number 1. I'm going to write down 1.0 and the number 1.1. So just like when we were doing decimals in section 1, it sometimes helps to think about there being extra zeros at the end of a number. Like this, maybe. You don't have to do 2 if you don't want to. If you don't want to do 2, you could do just 1 decimal. That's enough. The lovely thing about decimals is that we all kind of think in them naturally because of our money system. Right? This is $1 and $1.10. Okay, there's lots of numbers in between, even with money, that we could use. What are some numbers that are in between these? 1.05, right? That's the halfway point. What else? 1.06. We could even do 1.01 or 1.09, right? Now, not only that, but if you do think of them as having a third zero, you've got even more choices, right? So you could actually go with 1.001 and 1.062, right? The kicker in all of these is that it starts out 10. And then after that, it doesn't matter what you put in. It will be between the two values you have. So you have lots of options. Okay. The last example is the one that I was mentioning earlier. I couldn't remember if it was in this lesson or not. It actually has, it's 5 digits repeating. No, it's 6. 6 digits repeating. This is the one I mentioned before. All right, so some addition problems are easier to compute with fractions, and some are easier to compute with decimals. For example, 1/7 plus 5/7, that's pretty easy to compute. 6/7, right? Much easier than computing 14.142857 repeating plus 0.714285 repeating. These are the values that correspond to this. This is the number 1/7, and this is the number 5/7. So if you turned those into decimals and you computed them, you'd have those two repeating decimals adding together. However, if you had 0.4 and 0.25, that would be easier to compute in decimal form than 2/5 and 1/4, which are the equivalent values in fractions. So the question is actually this: describe situations in which you think it would be easier to work with fractions than decimals and vice versa. So I need a new screen. When is it easier to work with fractions, and when is it easier to work with decimals? You can either say it in the positive sense, when it has, or in the negative sense, when it doesn't have. Okay, so it's easier to work with fractions when they represent repeating decimals, right? I mean, I don't know about you, but I don't want to add those repeating decimals that showed up on the previous screen together. That wouldn't be good. It would be really ugly. What else? Okay, say that a little bit louder for me, Emma.
Decimals are easier when the denominators are different fractions.
I'm going to say are not the same. Okay, so we can put whatever we put in one place, we could put in the other. So I can say decimals are easier when the denominators are not the same from the fractions, right? Or you could say that fractions are easier when their decimals are the same, right? That's an equivalent statement. And I'd even say maybe that fractions are easier, maybe when they're not necessarily the same, but they're easy to find, right? Like if one denominator is 2 and the other denominator is 4, you're probably comfortable enough to deal with that. But if one denominator is 36 and the other denominator is 24, you may not want to. They're larger, they don't match, they're messier to work with. I think these hit most of the points if we rephrase them in the other direction even as well, right? So decimals are easier to work with when they don't terminate. You could say that, right? Or when they don't repeat, excuse me. Yeah, if they don't repeat, decimals are great. Fractions are easy to work with, like we just said a moment ago, when the denominators already match or they're easy to get them to match, that kind of thing. Any questions on that one? All right. So here's what's happening. You have group work for 7-2 and group work for 7-3. You have almost maybe like 18 minutes to work. I don't care which one you work on. It doesn't matter. You can work with a partner on whichever one you would like. But 7-2 will be due on Monday. 7-3 will be due on Wednesday. And I will post a video, half of the video of 7.4 for you to take a look at on Monday. Okay? And I'll get it posted hopefully after class today so you can do it over the weekend if you don't want to do it on Monday even. Okay? Awesome.